I want to make 2 points here. The first point is this. Most equations can't be solved exactly. That may not be the impression that you got when you were solving equations in middle school and high school. Basically, you were taught a technique, and then you were to use that technique over and over again on practice equations. And you might get the idea that equations are something that you can always solve algebraically. Those equations that were chosen in high school were very carefully chosen so the techniques that you had learned would work on them. Most equations, there's really no way to solve them exactly. Most equations, the best you can do is approximate solutions. And so if I give you an equation, something like, I don't know, e to the x minus, let's say, 3x plus 50 equals 0. Let's see. And I say solve that exactly. I don't think there's going to be any way that, you can try your algebraic techniques on that, but I don't think it's going to work out. And it's not just a state on the a comment on the current state of mathematical ignorance. We can show that there are certain specific ways in which it's just impossible to solve certain equations. The second thing I want to say might be to counter a thought that's already perhaps in your head, that why should we care in this day and age when we have such fast computing equipment at our fingertips about solving equations efficiently. After all, if you have an equation you want to solve, you can plug it into your calculator. You can just put it onto some app on your laptop or on your desktop, and it'll solve it in less time than it takes you to type it in. Certainly, it solves it in probably under a second. The thing is, solving equations is more important now. Solving equations efficiently is more important now than it has been ever before. It's much more important to you than it was, say, to your parents or your grandparents or so on. Half a dozen things you probably do before breakfast require a ton of equations to be solved. Not just one equation, but lots and lots of equations. If you bring the weather app up on your phone and you want to see what the weather prediction is going to be for that day, to get that weather prediction ready for your phone, a ton of equations are solved. Not just one, like a million. If you're downloading stuff off the web, you're downloading a video and it's encoded and it needs to be decoded and uncompressed, then that basically happens every single time you take a look at a YouTube video or a video on TikTok. There is a lot of coding going on, a lot of solving equations, and so efficient versus not efficient. It's the difference between waiting 8 hours for your video to be ready and having it ready so fast that you're not even aware of the delay. So solving equations efficiently is much more important to us now than it ever has been. So solving equations efficiently is increasingly important. Because as fast as your phone, as fast as your desktop, as fast as your laptop is, and it could solve an equation so fast you wouldn't even be aware of the time delay, having it solve 1 billion equations, how the efficiency behind that is important. You can't solve, say, 1 billion equations fast using a non-efficient method, whereas with an efficient method, it solves them very quickly. So I am just going to go ahead and tell you what Newton's method is, and I'll show you a little bit about how it works, and then we'll try it with an example. So, say we're given an equation. Equals 0. If it's not 0 on the right side, just start by moving everything onto the left side, and you'll just leave a 0 on the right side. So we can always put a 0 on one side of the equation. That's no problem. And for Newton's method, we need an initial guess for x. In this class, I'm always just going to give it to you. In reality, we need some way of coming up with an initial guess, just some place to start. It's not that hard to do, but we need an initial guess. We need an equation, and secondly, an initial guess. Any old number, we'll call x naught. We'll call it x sub 0. And what you do is you start with your initial guess, and then you produce a next guess, which is hopefully closer to the actual solution. And then you take that guess and you plug it back into the thing, and it gets closer. It just keeps getting closer and closer and closer until you have as many decimal places of accuracy as you need. 3 places after the decimal, 5 places after the decimal, however much it is you need. And here's how you get your next guess. So to get the next guess, which I'll call xn plus 1 from our current guess, x sub n, this is what you do. xn plus 1 equals xn minus f of xn divided by f prime of xn. So note, for Newton's method to work, the function has to be differentiable. It has to have a derivative. Sometimes, if you're working with non-differentiable functions, Newton's method is just not going to be the tool you use. Okay, let's go ahead and try this with an example. Solve, let's say, x cubed plus x minus 1 equals 0 to 3 places after the decimal. So here, we'll let f of x be our left-hand side. Actually, let me stop and wait till you finish copying all that down. Let f of x be x cubed plus x minus 1. So we're solving f of x equals 0. There we go. Oh, I forgot to give you an initial guess. So let's let our initial guess be x0 equals, how about 0? Our initial guess will be 0. We know that's not the right answer. If I plug 0 in, I get 0 cubed plus 0 minus 1. That's minus 1. That doesn't equal 0. So that's definitely not right. That's just a place to start. Now, I told you that most equations can't be solved exactly. This is an exception. This is a cubic equation. It's a cubic polynomial, third-degree polynomial. There is a formula to solve cubic polynomials, just like there's a formula just like the quadratic formula exists to solve quadratics. There is a formula to solve cubic polynomials. If you're wondering why we didn't teach you this in high school, just go ahead and Google it. You'll see that unlike the quadratic formula, which is nice and small and compact, the cubic formula is large. And there's absolutely no point in making you memorize it. The quadratic formula you can work out yourself using complete the square. It's a nice algebraic operation. It's very handy to use on a day-to-day basis. This one is more of a specialty item. You can look it up and use it whenever you want. So we could solve this algebraically, but we're going to use Newton's method instead. There's also a formula for the fourth degree polynomial. That's called the quartic equation. You can look that up too. And when you see it, you'll realize, again, why we don't teach it in high school. Okay, so what we're going to do is make a chart. So n is going to be the title of our first column. That's going to be the number of guesses we've taken. So our 0th guess is going to be 0. That's our first, our 0th guess. So x sub n, we said our 0th guess is 0. And then our next guess is going to be our previous guess minus f of our previous guess. So f of x is x cubed plus x minus 1. So minus xn cubed plus xn minus 1 divided by, now we're going to need to take the derivative. Taking the derivative of this is not going to be difficult. The 3 comes down, you write the x, the 3 becomes a 2, the x becomes a 1. So we have 3xn plus 1. Why xn rather than just x? Because what I'm doing over here is just using my previous guess for x to get my next guess. So our 0th guess was 0. Let's figure out what our first guess is, what our xn plus 1. In this case, n is 0. Let's find out what our next guess is. So what we do is it's equal to 0 minus 0 cubed plus 0 minus 1 all over 3 times 0 plus 1. So that's 0 minus basically negative 1 divided by 1. 0 minus negative 1 is 1. That's going to be my next guess. So my next guess is going to be 1. This number, just recopy it right there. Let's figure out what our next guess is. Let's figure out what guess number 2 is going to be. So it's going to be, now I'm just going to put a 1 in wherever I had a 0 before. So 1 minus 1 cubed plus 1 minus 1 all over 3 times 1 plus 1. I guess I could pull my calculator out at this point, but I don't think it's necessary. I certainly will by the next guess. So let's see. That's 1 minus, so that's 1 plus 1 minus 1, so negative 1. Sorry, we have 1 on the top. Yeah, we have 1 on the top, and we have 3 times 1 plus 1, 4 on the bottom. So it's 1 minus 1/4. In other words, 3/4. Let's just do this with decimals. 0.75. And I said 3 places after the decimal. What I'm going to do is actually carry an extra decimal place. When we do our computations in Newton's method, carry 1 more decimal place than I asked you for in your answer. So 0.750 is our next guess. So our second guess is going to be 0.7500. Again, we just take this number and copy it down over here. And we repeat the process, putting a 0.7500 in wherever we see an xn. So 0.7500 minus I won't pretend this is the most exciting thing in the world, Newton's method. What's exciting is it's efficient. So 0.7500 cubed plus 0.7500 minus 1. Oops, sorry, the fraction doesn't go into this. All over 3 times 0.7500. Oh, I forgot my square. Sorry. So that should be squared. Doesn't make any difference so far. Squared. Yeah, sorry. 3x squared plus 1. Plus 1. Let's see what that equals. Time to bring out the calculator. So let's see. 0.7500 minus, open parentheses, 0.7500 cubed plus 0.7500 minus 1. Divided by, oops, somebody's checking my arithmetic, 3 times 0.7500 squared plus 1, those parentheses. I'm getting 0.6860. Oh, wait a minute. Yeah, 0.6860. And just recopy that number over here. 0.6860. So 0.6860 minus 0.6860 cubed plus 0.6860 minus 1 all over 3 times 0.6860 squared plus 1. And here we go again. All this typing into the calculator, probably not very exciting, but at least not hard. Oops, I must have made a mistake. That can't be right. Let me try again. You guys are being very patient. That's better. 6, 8, 2, 3. See how these numbers are getting closer and closer together? We started off with, 0, then 1, then 0.75, then 0.6860. Now I have 0.6823. And we'll do the whole thing over again. 0.6823 minus 0.6823 cubed plus 0.6823 minus 1 all over 3 times 0.6823 squared plus 1. Here we go again. I'm getting 0.6823 again. Once this digit settles down and I can round, I can see that to the nearest 3 places after the decimal, it's 0.682. So the answer is 0.682 to 3 places after the decimal. So exciting? No. Efficient? Yes. Basically, the idea is this. If you're given some curve, y equals f of x, and you try to solve f of x equals 0, which is exactly what we're supposed to do here. What Newton's method does is it takes an initial guess. Let me draw this a little curve here. We're looking for this place. That's the real solution. That's where it crosses height 0. If you're given an initial guess, x0, what Newton's method does, when you do this process once, is it goes up to the curve, it draws a tangent line, and it sees where that tangent line crosses the x-axis. And that's your next guess. And then it goes up to the tangent line and sees where that tangent line crosses the x-axis. And that becomes your next guess, and so on. And you can see that as you keep doing this, where the tangent line crosses the x-axis is getting closer and closer to where the curve is crossing the x-axis. It's much easier, computationally speaking, to work with straight lines than it is to work with curves, which is why this is such an efficient method of solving equations. Are there any questions? In that case, have a great weekend, have a great Halloween, and I will see you all on Monday.
Have a good weekend. Thank you.
Bye. Happy Halloween.
Thank you. Thank you. Happy Halloween.